So good morning, everyone. Thanks a lot for joining. This is the second event in the Academic Fringe Festival, and this first edition is on crowd computing and human-centered AI. A very good morning to all of you who are joining us from places where it's morning, but as you can see, the speaker who's joining us today is Professor Gianluca Demartini, who happens to be in a place all of us would rather be in right now, Australia. So Gianluca Demartini is an associate professor in data science at the University of Queensland and in the School of Information Technology and Electrical Engineering. His main research interests span different fields such as information retrieval, semantic web, human computation, and crowdsourcing, and he's quite well known in these respective communities. His research has been supported by a series of different grants, and he has also won a fair share of awards, best paper awards, and such at notable conferences, both in the human computation community as well as in the information retrieval community. Gianluca is also a co-editor-in-chief for the Human Computation Journal. He is ACM Distinguished Speaker for several years now, and yeah, his reputation precedes him. So I probably don't have to say a lot more, but we're extremely happy and thrilled to have Gianluca join us here today. And he's going to tell us a little bit about bias in human-in-the-loop AI. Before I give him the stage and ask him to take it away, I'd just like all of you to take note of the fact that this meeting today, this talk from Gianluca is going to be recorded and it'll be available later on our website. So for those of you who may or may not want to turn your cameras on, it's worthy to take note. I'd also encourage all of you to make some noise in social media. As you can see, you can use Gianluca's Twitter handle here on your screens. If in case you'd like to share things from his talk right now or tweet to him later on, and don't forget to use the hashtag TAFF, which stands for the Academic Fringe Festival. So with that, it's a great pleasure to welcome Gianluca. Gianluca, take it away.
Thank you. Thanks, Ujjwal. Good morning, everyone. First of all, I would like to thank the hosts for organizing such an incredible series of talks. So very well done on the initiative. It's a very good opportunity, right? The fact that we are all moving online to get speakers from all over the world without any travel involved. All right, so as usual mentioned, what I'm going to talk about today is a bit of recent work we have been doing in the area of human-in-the-loop AI systems. And I will specifically mention several examples in which bias is being created and how this is managed in the systems we are building. Okay, so just before I start, let me give you a bit of a background where I'm coming from and what my own research bias is in looking at these problems. So historically, my background is in information retrieval. I've been building these information access systems that look at entity as an entry point to information, typically on the web. And then while building these information access systems, we started to investigate the opportunity to build human-in-the-loop systems. So really involving human intelligence together with the scalability of machines to process very large amounts of data in combination, so we can get the best out of both worlds. And when doing this, when building these hybrid systems, we realize what are the challenges of having humans in the loop in terms of data quality, in terms of bias, which I'm going to mention today. So we started to shift our research focus from building systems to really understanding how crowdsourcing platforms work, what are the implications of human factors in the system we build, and now not human factors as users of the system, but really as a component of our information systems. And then again, all this is reflected in data quality issues when we collect manually annotated data from, for example, crowdsourcing platform. How do we manage different levels of data quality. Okay, so that's a bit the big picture of the research we have been working on with my group. And this is what I will specifically try to focus today on. I will briefly mention a few works without going too much into detail, but of course I'm happy to go more in depth with specific pieces of work that we have done and there is an interest on in the audience. So in the first part, which hopefully will take 10 minutes or so, I will talk about bias in human generated data. Think of training data that it's manually annotated and then used to train machine learning models in a supervised manner. So I'll talk about a bit about that with a couple of examples and different types of bias. And then in the second part, I'll talk about tracking and using interaction behavior as a means to, again, measure and control this sort of bias, which is present in annotated data. Okay, so let's kick off with crowdsourcing. Crowdsourcing, as you may know, I know many people in the audience are much aware of it, is a method to collect manually annotated labels, manually annotated data and labels at scale. We can get very many human annotators to annotate a very large data set in a short amount of time and for relatively not so much money. The key issue, in my opinion, the key open research question in crowdsourcing is quality of the labels that we get back from the crowdsourcing platform. Because the key incentive on platforms like Amazon Mechanical Turk is the monetary one, crowd workers are motivated to be quick in order to maximize their earnings, and this often results in low quality of the annotations we get. So because of these people using crowdsourcing as a method to collect label data, they introduce a number of quality control mechanisms. Probably the most common quality control approach in crowdsourcing is that of gold questions. This means that if we ask 10 annotations for, say, 10 images to crowd workers, 1 out of 10, we have a ground truth label available. So we can compare the crowd answers against the ground truth answer to check for quality, right? If the worker answering these 10 questions correctly answers our question 7, for which we know the correct answer, then we trust all the answers the worker is giving us. If the worker doesn't correctly answer question 7, we may want to discard all the answers provided by this worker. So the key for gold questions to work is that the workers are not aware of which out of the 10 is the gold question, so they try to answer to the best of their ability to all of the 10 questions. So the requirements are that they are indistinguishable by workers, but the issue is that also few of them are available, right? Because if we have the correct answer for all of our items in our dataset, there is no point to collect more labels. So the assumption is that a small percentage of our dataset can be used as a gold question because as a ground truth label attached to it. So because of this property, we need to repeat the same gold question across different tasks and show it to many times to different crowd workers. And that's not a problem by itself because different crowd workers will see the same gold question many times, but they don't really talk to each other, so they won't know which one are the gold questions. But if we are assuming that these crowd workers can actually share information, and so let's imagine a group of colluding workers on a crowdsourcing platform that share the questions they are observing. So imagine a browser plugin which is taking the crowdsourcing task with our 10 questions and sending it to a server to compute the frequency statistics of how often a question is observed by this group of workers. If that happens, which is a very simple technical thing to set up, we can get something like this, right? We can plot the frequency distribution of questions, and then we see that gold questions are shown more frequently than non-gold questions. We will still observe a non-gold question, a normal question, more than once, because that's by design of the crowdsourcing experiment. We collect multiple labels for the same item, but again, gold question will be repeated much more often. So by the property of the data set and of gold questions, if this group of workers can share frequency information of the questions they observe, it becomes very easy to know which are the gold questions in the task. And if this happens, obviously the workers can only answer one question carefully, and the other 9 in the task, they don't need to answer it carefully, to again optimize the time they spend on completing tasks and getting money out of the platform. So if this happens, crowd workers can save time, which means getting more money in an hour, because they are able to do more tasks. In the green line here shows the time required by crowd workers to complete tasks if they know frequency information of questions, and therefore they have an estimation of which are the gold questions. And you see, the more information is available, the more the gain of time and money becomes, so the bigger the gain becomes compared to an original experiment and how long it takes to do a task. So this is an interesting type of approach, very simple technically to happen, and gives more power to workers, right? We have seen quality is an issue, gold questions is a common quality control mechanism in crowdsourcing, but a group of workers can, in a way, go against that and automatically detect the gold questions and then break the entire quality control approach in crowdsourcing. There are ways to deal with it, but the more interesting discussion here is what are the implications, right? Of course, at the moment, the entire quality control effort is in the hands of the requesters and the platforms, and it's really pushed onto the workers who don't really have any power to complain against quality control, to decide which quality control should be made. So these type of solutions, again, rebalance a bit the power imbalance in crowdsourcing platform. But for our discussion about bias, the interesting observation is that it creates bias, right? If there is such a group of colluding workers attacking the gold question quality control mechanism, they obviously will introduce noise in the data which is being collected, and there is no way for the requester and the platform to know, because on the gold questions they answer accurately, but they will not on the other 90% of the labels they provide. So it creates a data quality issue in the data set, in the label data set we collect, and then which we may use for training models and so on. So this is the first example of bias, right, that we might have in manually annotated data that we collect from humans. Let me tell you about another example. This is about the crowdsourced knowledge graph. So we are moving away from paid crowdsourcing platforms like Mechanical Turk to another type of crowdsourcing project, in this case, Wikidata, which is one of the Wikimedia Foundation projects. This is a collaboratively edited knowledge graph. So people can go online and add entities to the graph, add relations to the graph between entities, or modify any information which is there. So either nodes or edges in the graph. Another interesting property of this is that it's not a static graph. It's actually evolving over time. In every every moment, editors, users of Wikidata go to the website and modify the graph. So it's a constantly evolving graph. And again, we have a few plots here that show how people edit the graph. So we look at the entire editor population, and we look at the work they do on the graph. So as you can imagine, the contribution distribution is a power law. So very few items have many editors, and the majority of items, right. So very few items have many editors, and the majority of items have just a few editors, right? No, not even that. Right, so this is how many users an item has, right? So very many items just have one editor, and very few items have 300 editors. Same things for the number of edits done by users. Very few users do many edits. The majority of users do just a few edits. And that's common really in all crowdsourcing projects. So a few observations that we have done when looking at those editors who do edits on the graph for a long time, several years, compared to those who stop doing contribution, is that they manage to make it an habit, right? They will do it in the evening, they will do it every weekend, and also they try to make it to diversify, right? Not to do always the same, but over time, they try to change the type of edits they do. For example, they first edit all the major mayors of cities in Germany, and then they move to country populations, and then they move to something else. So they focus on a topic for a while, and then they shift to diversify. So let's go back to our point of bias, right? Why does this create bias? Well, if we have a small percentage of the editor, the contributor population, who have this long lifespan in the project and do very many edits over a long period of time, they obviously have a significant contribution to the data which is stored as compared to the rest of the editor population. So here we looked at more than 30 million different editors, but of course, just very few of them have contributed the majority of the graph, which really creates a bias, right? It makes the data not really representative and makes it not, the coverage of the data may suffer because of these skewed distributions of contribution. So to reiterate the point of this coverage issue due to this, so this is the cause of the problem, and now this is the problem itself, right? If we have this knowledge graph, which over time keeps growing, the question becomes which part of the graphs are growing and which are not. And this is, of course, choices that the editors, the human editors, are making on completing one part of the graph and not on the other. So in order to understand that, the question we need to answer is how complete is the knowledge graph, right? And specifically, we are looking at class completeness. So the example here is, we have a knowledge graph which includes cities of Germany. Do we have them all? And if not, are we 80% there or are we 99% there? So in order to answer this question, do we have all the entities of a type in the graph? We need to know how many are the cities in Germany, right? What's the total number? Which formally means we need to know the cardinality of that class, cities of Germany. If you know that the cardinality is 100 or maybe 1000, and we know that in the graph we have 800 entities of the class cities of Germany, we know that our completeness is 80%. So the problem becomes how to know the cardinality of a class in a knowledge graph. It's easy for classes like US states, right? We know exactly how many US states we have, but it's difficult for other classes for which there is no ground truth, again, available of how many entities of a class we have. So what we did here is we looked at a method that is estimating the cardinality of a class by leveraging observations over time of items of that class. So in this example, we are trying to estimate the cardinality of the class monument, and we are observing over time 3 mentions of entities in that class, because these right, so the monuments are this one, this one again. So we only count once when we found a monument, an entity of that class. So based on these observations over time, we use statistical methods that will estimate the cardinality of the class based on how often they see the same entity. Again, this is the same. It was originally proposed to estimate how many lions there are in the savannah. You don't know the number, but you can capture a lion, you tag it, you let it go, you capture another one, and then you start recapturing the same lions because you tag them, so you know they are the same. And this allows you over time to estimate how many lions there are. And this is how the estimate goes, right? The more observations you make, the more your estimate will converge to the ground truth. So this dotted line is the ground truth of how many paintings Van Gogh has made, around 800 something. And then these estimators will, with enough observations of paintings over time, they will converge to the correct number. So in this way, we can actually estimate how much of a knowledge graph is missing, and again, measure the level of bias that we have now. And in a knowledge graph like Wikidata, this can help in focusing human effort in specific parts of the knowledge graph, which have high level of incompleteness as compared to others, for example. All right, so the third example of bias I want to talk about is the political bias. So this year, also thanks to Facebook, we worked on misinformation and truthfulness judgments. We used it, we have done it using crowdsourcing. So what we did is we asked the crowd workers on Mechanical Turk to tell us whether a statement made by a politician is fake news or not. We done this using different data sets, using different judgment scales. We tried 3 levels, true, false, and in between, up to 100 levels. So you have a slider, you can slide how fake something you think it is. And statements look like this, right? A politician saying something in a specific context, and then the assessor, the annotator, has to say this is fake or this is true. We only recruited US workers based in the United States, and we showed them US political statements, but then we also showed them non-US political statements to see if there was any bias because of the knowledge or location of the statements. Okay, so that was the experiment. Let's look at what happens. This is just one summary plot that is basically saying that it works. It is comparing ground truth expert judgments. So these are 2 data sets. The left one is the US data set, and the right one is the Australian data set. On the x-axis, you have the ground truth fact checker, the journalist ratings for the statements. And on the y-axis, you have the crowd workers from Mechanical Turk judgments. And you see that there is a correlation, right? The extremely fake statements get the lowest score by the crowd. And then the more you go towards the true one, the true statements, they get a higher score from the crowd. So once you start collecting multiple labels for a statement, you aggregate, you do quality control, it does work, right? So what you can do is you can complement expert fact checkers with non-expert crowd workers to collect very large manually annotated truthfulness data set. But again, let's go to the bias question and let's look at this data more in depth. One thing you observe is a political bias effect. So we really wanted to answer the question, can non-expert crowd workers do what fact checkers do? They cannot do the same, but they can come up to the same at the same truthfulness rating as experts. The issue becomes that if you ask a subset, if you look at the answers provided by a subset of these crowd workers on a subset of the statements, you will see a big difference, right? This plot shows how crowd workers answer based on whether they self-reportedly voted Republican at the last election or Democrats at the last election on the same statement done by a Republican politician. So you see that at all the levels of truthfulness, from extremely false to extremely true, according to experts, while the trend is the same, you see a clear difference at all levels between the groups of red and blue workers. The red workers at all levels are more generous than the blue ones on statements by red politicians, right? So there is this political alignment, right? If I'm reading something which is aligned with my political thinking, I'm prone to believe to it more, no matter what the truth is. Not very surprising, but it's a clear issue if we are collecting training data to train an AI to do fake news classification by itself, right? It really depends who the people are who label the data, which is then used to train an AI to run on Facebook and remove all fake news from that. That's really an important issue, right? It's important. So what this means, what this result means, is that we must be very careful in the way we select the annotators to annotate the data we use to train models. It's not just about which are the instances, but also who are the annotators. Okay, so this was the first part. In the second part, I'll try to keep it short as promised. I want to talk about interaction behavior. So I'll mention the type of data we are using here, and then a couple of examples. I might skip one to give you an idea of the possibilities that can be can come from there. Okay, so when I talk about user behaviors, I mean users interacting with the web system and doing actions like clicks, keystrokes, keyboard shortcuts, every action that can be observed on an HTML page. So technically how this works is that in an HTML page, you embed some JavaScript code. This JavaScript code will send messages to a server, and the server will store all interaction data. So let me give you one example of how this interaction data can be used. One example is crowdsourcing. You have a crowd worker interacting with a crowdsourcing task, which is indeed an HTML form, right? It is just an HTML page in which you can embed your JavaScript and send messages to your server. So typically what happens is that crowd workers approach a task, do a few questions like we have seen at the beginning, they completed the task, at the end, they get the reward they deserve to complete for having completed the task. What really happens is that sometimes workers start a task and at some point in the middle of the task, they decide to drop it and go back and look for something else. When this happens, the requester doesn't know anything about this because unless they reach the end, the requester will not receive any of the answers. And the platform doesn't receive any answer, right? Because until you submit your web HTML form, nothing goes back to the server. So what we did is we tried to observe and measure this phenomenon, right, of workers starting a task and dropping before finishing And we can do this by injecting the JavaScript and observing what workers do before finishing the task. So we are actually have a way to observe this phenomenon which is otherwise invisible. And sadly, what we have observed is that this is a huge phenomenon. In our experiment, we have measured the equivalent of more than 3 months full-time work, which was not observed and not rewarded by the platforms and by the requester, which is big. Again, over 5,000 workers, but still overall, it's a big problem. Also, as you would expect, most of the workers will drop early in the task, so the lost time is not so much. But still, if you start summing up all the time which is lost and not rewarded, it's a very big phenomenon. Okay. So this was just an example of how you can use this type of data. Let me just generalize this a bit, right? If you collect all information about all the clicks and all the interactions that users have with systems, you can start using this data to create user models. So what we did here is to use neural networks in order to build embedding representations of this interaction data. What happens here is that we collect interaction data like this. They are all clicks or users typing some text or doing shortcuts, keyboard shortcuts. We consider these single actions. We can build n-grams of sequences of these actions, right? These actions happen in a sequence. First you copy and then you paste and then you edit what you pasted. So we can define n-gram sequences of these actions and measure frequencies of these actions and do magic things with this type of data. So what we did is we build a vector representation of this user interaction behavior. And with this, what we can do is we can start comparing users one each other, see how they interact with a task or with the system, how things change over time. For a user interacting over a period of time, you can look at how the interaction behavior is changing as the user is adapting to what they are trying to do, and so on. So you can do very interesting observations of what users are doing. Once you have embedding representation, the classic things everyone does is TSNE projection. So that's what you get in two-dimensional projections for this highly dimensional vector space. On the right here, you have the Wikidata editor dataset and their interaction behavior. So here we have two groups. The red ones are the ones which are very active and have a long lifespan of edit history in Wikidata. The blue ones are the ones who are less active. If we look at the interaction behavior space, we see that the blue ones tend to have very similar behaviors and then they drop. The red ones who have interacted for a long time, they actually have a much more diverse behavior across the space. So these people have learned how to be productive in very different ways. The blue ones didn't, and they all, in a way, fail in the same way. On the left, you have different things for a crowdsourcing task. You have actions like change a document and copy something and then find in the page something. This is a sequence of actions. And this is closed in the space to a duration of 24 seconds. You have in other parts of the space durations of 2 minutes or even longer, right? So this task, which has a long duration, is associated to sequences of changing radio button decision, changing again, replacing the text that was there. So a lot of modification of the answers, which correlates with a long task duration. Short task duration, you copy and paste something and you submit. Again, you can do all these interesting observation of different type of approaches and behaviors done by users. Okay, so this was the quick overview of some of the recent works we have been working on. I guess to summarize it with one picture, that's a bit what I've been talking about, right? The bias which is coming from human annotators into label data to then train supervised models. And then on the other side, you have a user which also comes with their own stereotypes and bias, but you can log all these different interactions, user to system interaction, and then trying to understand how users are different one another with the goal of obviously personalizing, right? So the question here becomes, if you are aware of the bias in your data and in your model, but you are also aware of the differences and idiosyncrasies of your users, how do you present your information in the best possible way to the user? Do you match those bias and stereotypes? Do you try to break the bubble and show different things from what they expect? I don't know the answer to that. So the last point, and I really want to leave you with some open questions rather than answers, is what's from here? And what I see next is really the combination, not just of human and machines, right? That I said I've been looking at for a while, but really how to combine different type of agents to solve the same problem. So thinking of fake news, for example, right? We have the fact checkers. We have shown that crowd workers can do the task at scale. We have automatic models that work in a supervised manner, which are very quick to run at scale. So how can you combine all this together? And this is my list of open questions, right? Who should do what? If you have experts, non-experts, and AI, whom do you allocate annotation tasks to? Or even how you combine, right? You could imagine having a bit of a workflow where a president is writing something on Twitter, and then very quickly, real time, an AI can automatically classify that in true or false and label it. And then later on, maybe 12 hours later, expert fact checker starts to do their forensic processes and then come up with a better label for that. Right? So you can actually use multiple methods together in combination in order to get the urgency, the scalability, the quality all together in an hybrid system. Of course, this vision comes with question on how would people actually work together with AI? Would they trust the decision of the AI or the selection done by AI for them to work on and so on? Anyway, I think I'll stop here, and I hope you enjoyed this quick overview of some of the recent work we have done, and I'm happy to get questions if you have any.
All right, thanks a lot, Gianluca. That was a really exciting talk, and I'm sure our audience enjoyed it quite a bit as well. So feel free to type in your questions if you have any into the chat space, and we'll relay them to Gianluca. Yeah, so I see that we have some coming in. So Zihang here has a question, but since Zihang also has privileges, perhaps you can ask Gianluca this directly.
Yeah, thank you. It's a great talk. Thank you, Gianluca. So I have a question in terms of the fact check. So maybe I didn't get the details, but how did you find workers with different political views from Mechanical Turk? Like, do you first find the workers with different political view and then do the experiment, or this is the like natural distribution of political views in Mechanical Turk?
Right. Yeah. So we basically ask them, right? At the beginning of the task, we ask a number of questions about the demographics, and one of them is what they voted at the last election. So obviously that is self-reported, right? It's what they told us they voted for, which may be correct or not. But based on that answer, we can color them in blue or red, and then we can look at the answers they provide based on which group they belong to. So that's how we got the data about their political background.
Yeah, thank you. Thank you.
Suzanne, would you like to ask your question as well?
Yes. Gianluca, thanks for the very nice talk. I am a PhD student with Christina Sarasua, actually, in Zurich.
Yeah, I remember. I think we met in Zurich.
Yes, we did. I have a question regarding the use of crowd sourcing and crowd working in general, as in because of Corona, many people who did in-person experiments now cannot do this anymore. And I've seen a lot of researchers instead go to platforms such as mTurk and Prolific to instead do their experiments there, given that they then still have access to a certain, crowd to be able to run their experiment. So my question would be, for those researchers, what do you need to be aware of in terms of how to phrase your experiment differently, maybe in terms of biases that you get in terms of samples? So what do you think about this general tendency, and what would you advise those people essentially?
Yeah, no, that's a great question. We do a lot of experiments on crowdsourcing platform, but we do a lot of experiments in the lab. We like user studies, we use eye tracking. So I think that's, in my opinion, the key difference, right? If you do a user study in the lab, you have a different access to your subjects, to your participants. You can observe them, you can talk to them, you can interview them, you can measure things that otherwise it's not easy to measure. The type of task is also difficult to port usually in a crowdsourcing platform, right? In my experience, the typical duration of such studies is around an hour or so. The typical duration of a crowdsourcing task is around 1 minute or so. Obviously, it is possible, right? I'm not saying it's impossible. You could, and we do, potentially run a crowdsourcing task that lasts 1 hour. You can potentially interview crowd workers using what we are using now, or Skype. So technically, it is possible, right, to give up the lab study for a fully online experiment. It is more difficult, I guess. It is difficult in the type of observations and data you can collect. I don't think the sample bias is really an issue. You still have a sample bias if you do a lab study where the majority are students, university students. Here you will have actually probably a more diverse sample than just 20-something university students. So yeah, I know this has been a trend this year, and again, we are doing a lot of replication studies to compare the lab and the crowd. In short, I think it is possible. You just need to know that you might get different type of data and observations, but obviously the crowd comes with the advantage of scale, right? Instead of having 20-something participants, you can have 200 or 2,000 relatively easily. So it's different. It's different, but you can answer research questions as well. So this year and maybe still in the future, it's a method that could be considered widely.
Yeah, thank you.
Thanks.
Thank you. Do we have any more questions? So perhaps while you think of more questions to ask Gianluca, I can ask one myself. So Gianluca, towards the end, you nicely discussed a few open research questions, and what caught my eye was when you spoke about different levels of control when experts could be embedded in this new human AI framework. Could you say a little bit more about that, about how you pose it as a need for self-explainable human-in-the-loop AI tools?
Yeah, I don't know the answer. I guess that's the question we need to all think an answer for. Yeah, so experts should do what experts are good at, right? They are very expensive, so it makes sense to optimize the use of the expert human resource as much as possible. how to do that optimization, I'm not sure, right? But we want, again, a couple of examples. Data scientists are spending 80% of their time on data cleaning and preparation, but they are machine learning, algebra, matrix operation experts. So that's not an optimal use of expert resources. If you can allow data scientists to focus on what their skills are about, it's a better use of the resource. Journalists, fact checkers, they spend a lot of time deciding what to fact check before fact checking it. But they are very expert in going, find the sources, the forensic, for then saying that's incorrect. But a lot of time is wasted in, out of 1,000 tweets that a president has made, which one should we spend a week to fact check? Again, they can be helped, right? They can be helped with AI, they can be helped with crowdsourcing in order to use their time in a better way. I don't know exactly how, but that's the goal.
Thank you. Any more questions, Jay?
I actually do have one. Thank you, Gianluca, for the great talk. So I was thinking about similar questions to what Sihan and Ujra was asking. So in your study of the political bias, you have, I mean, we all know that there are two types of people there, right? So I was wondering if it's possible to estimate the number of different, the different potential types of crowd biases when, you know, when the different types are not predefined. If it's possible, like, I mean, it looks to me that it's similar to this lion problem, estimating the number of lions, but only that here we are dealing with biases in the people, right? So that seems to be more challenging, and I'm not sure if so. What would be if or not there would be a way to do that, and if so, what would be the way? And perhaps experts could also be useful in this case. I was wondering, what's your thought?
No, that's a great point. So a couple of observation is that bias is hierarchical. There are several taxonomies of bias. So that's one point. And then obviously different people will belong to different groups in this bias hierarchy. So if those are correct assumptions, then in my opinion, the better approach, rather than top-down defining this taxonomy of bias and trying to fit people in, it's more interesting to take a bottom-up approach in which you take some data, for example, this interaction data, behaviors, or you look at what people are doing, and then you start to group them together, right? Those who have similar patterns will flow in the same groups, and then slowly you build it's like a hierarchical clustering that incrementally you start building up your groups using some sort of similarity concept. And this might give you an answer, right? Might give you how people are different. I guess bias is really about the differences that exist between one individual and another. So really, if we are able to measure the differences through some metric, then we are able to know which types of bias there are.
So data-driven approach.
That's my bias.
Perhaps another question from me, Gianluca. So you talked about biases in human-in-the-loop AI in general. I was wondering whether, you know, across the wide landscape of works that you've been carrying out, have you ever come across instances or ideas that might want to permeate desirable bias in particular systems?
Yeah, I'm not sure about desiring for a bias, but what I think we might want to do is to manage bias, not even mitigate, right? As you said, in some cases, you want to keep a bias because your users are more engaged if there is a bias, because that's what they want, that's their bias. So you are matching the user desire. So it would be nice to have a system where bias can be managed, right? You have a switch, you say, I want more of this, more of that. And that allows you to remove bias. So you do it as balanced as possible, but you also have the ability to push it to an extreme or the other. And then you see what happens, right, with the user engagement. We know all these internet companies are optimizing for user engagement. So the question really becomes what maximizes engagement in terms of playing with these bias dimensions, right? And pushing content more on one side or another, and then you see if that's useful or not.
Great, thanks a lot. So I think I'd like to take this opportunity to thank Gianluca once again for an amazing talk that was quite engaging. If there are no more questions, we can all collectively give Gianluca a virtual round of applause. In other times, this would be a resounding moment, but right now, let's just make do with virtual applause. Thanks a lot, Gianluca, for your time and for taking all our questions. We look forward to seeing you around. And
Thank you. Yeah, go on.
And for everyone else who's still around with us, I look forward to seeing you in 1 week's time. The next talk we have is from Mihaela Borverianu from Microsoft, and she's going to tell us a little bit about guidelines for human-AI interaction. Thanks a lot for joining us. This is the Academic Fringe Festival, and we'll see you in 1 week from now. Thank you, Gianluca.
Thank you, everyone.